methanol, we will get only about 15%. So it means that we have a very high driving force here for making or using your Japanese principle to drive the reaction over the product space. This has, of course, been recognized by industry a long time ago. And already in 1981, Michael Bishop, they patented the process where they took the effluent gas from the methanol reactor and took it directly into the methanol to hydrocarbons without any intermediate separation. A similar process was patented by European Hydro in 2000, and making them olefins while the first unit gasoline. So this was all that happened from 1981 to 2001. And then here, Kais was the first to patent a process where both reactions were carried out in one reactor. And since then, several other players have patented similar concepts, like Dow and Chevron and Zeotype, Dalian Institute, of course, the Institute of Chemistry. So we see that from 2001 to 2010, there were 3 patents. The next decade, there were 7 patents, and now in 21 to 22, we have already had 7 more patents. So there is an increasing interest based on that. So the scientific community learned about this process mainly when, as we saw from the previous talk also, the BAO group and the one group from the Dalian Institute published these tandem systems, zinc chromium oxide and catalyst, 400 degrees and syngas feed. And they could demonstrate that they will get a very high C2C4 olefin selectivity, some hydrogenated C2C4 and some heavier products, and very, very methane compared to this Anderson-Schultz Flory distribution of the Fischer-Tropsch process that you see here beside. We also see here that from the same study that over more than 100 hours on stream, there was a very stable CO conversion. So, this was encouraging. But we also see that the CO conversion is relatively low in this process. And among the products, we see that 45% of the products are actually CO2. So the question is whether this is now a general feature of the process or whether it's just this study. Now I took a look in literature, and I found one study that with the diluted syngas over 3 zeolites combined with the zinc zirconia methanol catalyst, and then compared it to other MPO studies of the same steel types in literature. So it's not the same studies, it's not the same group, but still we can compare. And if we now look at the initial hydrocarbon formation rate of these systems, we see that systematically MTO gives much higher rates of product formation than the syngas process. So we see it's a general feature here that the tandem process has much lower conversion rates. And that means that you need to have a bigger reactor or you need to have more respect, of course. Now, if we, on the other hand, if we look at the activity loss from those studies, after only 6 hours on stream, we see that for this MTO operation, it was 100 or 70–80% loss of activity only after 6 hours, whereas the syngas operation lost very little, about 10%. So that was very, those are very stable. And that is a big advantage because you then could go from this fluidized bed operation with the continuous regeneration and to more fixed bed operation for these processes. And then we see also that the initial methane selectivity is of course then higher for the syngas process, and this could be due to the presence of a hydrogenation catalyst, or it could be aldehydes. And we also see that in general the C4 paraffin to olefins ratio follows the same trend. That syngas operation with high hydrogen pressure in the bed, they lead to more paraffins. Now, the reason could be related to the co-catalyst, the methanol catalyst, but it could also be due to the gas composition, of course. And we see here a study from the U group where they co-fed high pressure CO to methanol over psilocin-5 zeolite, and they found a large increase in the selectivity to aromatics and a decrease in the selectivity to alkenes. Normally, those are linked so that you have hydrogen transfer to form alkane plus aromatics when you do the NPH reaction. But with CO co-feed, they found that they had much more. I'm sorry, I'm doing this wrong. They had much more of the carbonylation reaction, so they actually promoted a new route to aromatics formation and suppressed the ordinary route via alkenes. Then there was a study by Professor Bahn when they co-fed high pressure hydrogen, and they could see for the activation and deactivation of the process with methanol over SZ13. They would have a much more stable performance when they embed hydrogen. And finally, there are more studies that have studied the addition of water to the process or to methanol. And what has been found in all those studies is that there is an unselective retardation of all the reactions going on due to competition for the Brunstad acid sites with methanol. And this again leads to a more favorable feed modulus, and that means that you have slower deactivation in the process. Okay, now to our results. So we have studied this reaction now for 4 years in a new project together with several partners, as you can see here. What we are aiming here is to have a bifunctional catalyst in a single reactor, and we want to make fuels and chemicals, and more correctly, we want to make propane and we want to make propylene. So we have studied many catalysts in this consortium, but today I will focus on one of them, and that is the zinc zirconia catalyst with MAVO18 catalysts as the methanol converting catalyst. And if we focus first on this MAVO18 catalyst, it is a cavity window structure with a distorted cavity compared to the Sappho 34 structure. And we made 3 of those. We have here the Sappho version, we have the magnesium alpha version, and we have the cobalt alpha version. And we made them in similar size that you can see. And then we see from IR studies, we can see that the peak for the Brunstad acid site, it is shifting from the cobalt to magnesium to silicon. And by that you can see that the acid strength is increasing downwards here. Another thing you can notice here that I'll come back to later is that we have very small peaks for the Brunstad acid site in this case. These what materials that have been stored on the bench for a while. Another thing that we can note here is that the density of the heteroatom in the structure and the amount of Brunstad acid sites that we see in the structure is not 1-to-1. We see that we have fewer Brunstad acid sites than we would expect, and this means that there could be extra lattice framework, extra lattice species in the framework. Now, when we test this catalyst for the methanol to hydrocarbons reaction, 350 degrees, ordinary condition, we see that typical feature of deactivation over 12-16 hours in stream. They are quite similar. We also have the same variant here. And we see that the product distribution is also quite similar, with mainly propane being formed. But we also see that the silicon version has a higher propensity of forming methane and lower for C4 than the magnesium we have. And this is partly because we have a slight distortion of the ring where that hinders diffusion, which is a bit larger with the M2 plus ions than with silicon. So the first thing we did with this material was that we subjected it to voltage studies. And in the first one, we see here we have methanol with nitrogen over subweighting, and we see the expected deactivation there in black. When we now add high pressure hydrogen, we see that we have much more stable operation, but still deactivation. This is, as we know from each. And then what we see if we coated CO or CO2 together with hydrogen, we have an intermediate situation. Doing the same thing for the magnesium version, we see that the additional hydrogen and also the hydrogen CO and CO2 mixtures, they give a very stable operation. If we now next look at something that was very exciting to us, it was that when we look into the distribution, we see that, well, we have the C2, C3, C4, C5 plus, and then this is C5 and C6 plus. These are mainly olefins when we don't have any coating. When we coated hydrogen, you see the pattern part here, those are the saturated products. And then when we coated CO with hydrogen, we see that CO actually suppresses the hydrogenation of olefins. And this is, of course, very important when we want to develop a process for making protein. And we see that with CO2 coated, then we see that there is also somewhat a suppression, but it's because the hydrogen pressure was lower. We have verified that with other experiments. And then we see for these other two variants, the magnesium and cobalt variant, we see that it's exactly the same. CO coated is suppressing the hydrogenation of the olefins, while it is maintaining we wanted to confirm that it was really a suppression of the hydrogenation reactions that we could see. And we did this with feeding either hydrogen in nitrogen or hydrogen in CO over the same stable catalyst. And we see that the amount of ethane being formed is much lower when we have CO presence. Now, we know from theory work that's done in the Hibitz group that the hydrogenation of olefins and other components happens by heterolytic splitting of a hydrogen molecule over a Brenzler acid site and its neighbors. And this is also what we think is happening here. So the role of CO in this context, we don't know, but of course we can speculate that CO will absorb on one of these oxygens and therefore outcompete the hydrogen sorption and reaction. Now, when we have seen now that there is a difference between the cobalt and magnesium, so the M2 plus containing material and the SAPO material, we want to elucidate in more detail what is going on in these materials. And what we did was for our colleagues at the University of Turin, the Silvia Bonita group, they were studying first the acid sites in the cobalt alpha 18 by IR spectroscopy. This is an in situ calcined sample, and we can see here that the Brenzler acid peak is much more well defined than it was on the scored sample. And then we see that when adding CO at liquid nitrogen temperature, we see that we have a large peak growing up here, while the Brenzler acid peak is depleted. And then we also see that when we afterwards evacuate, we see that there are two remaining peaks here, a little peak, which was part of this Brenzler acid peak, and another one at 2,206 radical centimeters. And this 2,183 reciprocal centimeter peak is typically due to the absorption of CO on the relative acid side. But since we saw this very persistent part here, it means that there must be another site that is also giving the same signal. And this was allocated to CO absorbed on this lower in cobalt, which is part of the structure. So it's actually cobalt as a Lewis site, which is present here. And then we have another site, and that is CO, that is ion exchange onto the Brønsted acid site, so replacing the proton in the structure, and CO is absorbed that, and that has been seen also in other contributions. So when we of course, with this cavity window structure, we cannot really study the reaction mechanism because what is diluted out of the crystal is not representative of what is inside. And so we just turn to, I just cite to you some previous work that has been done. We know that if we have a higher acid strength, then we will have some impact. Typically, if we increase the rate of all those Brønsted acid site catalyzed reactions like alkene, iron methylation, hydrogen transfer reactions, cracking reactions, and what we have seen also from theory from Felix Stutz and co-workers, they made theoretical studies of alkene and benzene methylation, and they found that the alkene methylation is much more sensitive to acid strength than arine methylation. And the reason for this is that the transition state of benzene methylation is much more stabilized by the lattice, by the van der Waals forces with the lattice than the transition state of alkene methylation. Another thing that we have seen is that the hydrogen transfer reactions that convert alkenes to aromatics and aromatics to fall, they are also more sensitive to acid strength than the methylation reaction, which means that we see saturated products when we have the same conversion. But because the methylation reactions are really the propagation reactions are much more abundant than the hydrogen transfer reactions, we saw that with the VME Heteroatom launched for straight similar channels, then we saw that we had higher activity, higher alkene selectivity, and higher turnover number before the activation of the one with the higher acid strength. So we can take this insight with us. Yes, we have one other point which I also think is relevant here, and that is that it has previously been shown from the Gottom's group in Health and in co-workers that if you ion exchange these alkaline earth metals into silicon 5, you see much of the same effect that we see with the heteroatoms incorporated in the lattice. That means that you have, of course, now lower activity because they are covering some of the Brønsted acid sites, but you have a higher alkene selectivity and higher ton than you have for silicon 5 below. So they are acting as Lewis acid sites also in this structure. Yes. So now we turn to spectroscopy studies during the initiation or the early phases of the MTO reaction over cobalt alpha 18 and SAPO 18. This also in Boniga's lab. And what we see here is that with the addition of methanol, the first thing that appears are the methoxy species, as we would expect. And then, adjacent to that, you see that there is CO, space CO in the quartz that is formed from the methanol that we can observe. And we see that they are abundant throughout the 4 hours of reaction. We also see that there is formation of linear olefins as you can see in red here. And there is with time also formation of aromatic compounds, but it is the linear olefins that dominate in the sulfate-18s. If we now go to the cobalt alpha-18 structure, then we see that it's the same thing. We have the toxic species are formed, and we also see that CO is formed very rapidly in the first 16 seconds. But then something interesting happens because this CO signal, it is declining very rapidly. So CO seems to be consumed in this case. And we also see now that we do form linear olefins, but we also see that we have much more abundant formation of aromatic species in this cobalt alpha-18. So that means that the presence of this cobalt, that is always the selectivity of the reaction. And especially what we can then conclude here is that CO, sorry, I'm used to this pointer. The CO it's performing then a carbonylation reaction with the methoxysides, forming C2 species, and thereby inducing this reaction that we saw from the with the formation of aromatics directly. And one very interesting feature here is, of course, that we don't see any sign of CO coming out from the structure. Okay, so let's go now to the co-field studies, the CO2 hydrogenation, and we start with the. I have to train. We start with the standalone methanol form catalyst, zinc oxide zirconia. And this is a catalyst where you have detailed XRD and SAS studies. They have shown that the catalyst we have consists of minor small clusters of zinc oxide distributed in zirconia. And the reaction is happening at the interface between these two phases. And so the zinc oxide, it is with the reducing conditions that we have under CO2 hydrogenation, then the zinc oxide is depleted in and the zirconia is caught up in oxygen, and we have a heterolytic cleavage of hydrogen on the zinc oxide, and then CO2 is absorbed on the in the zirconia cluster, and then they react then at the interface. And theory predictions, they say that that methanol is the preferred product, and this is what we see also experimentally when we test. So this is the increasing conversion of CO2, and we see here the selectivity to methanol, which is decreasing with increasing conversion of CO2, and then we see the CO selectivity coming up. And you see already at about 5% conversion, these products are at equilibrium. They are following the dotted line, which is the equilibrium here. So, methanol is the first product, but it's limited by equilibrium. So what happens now when we test this catalyst, the zinc zirconia, together with the MAPO-18 catalyst? Well, first we see when we test alone, we have 7.8% conversion of CO2. We have about almost 50% selectivity to CO, and we have about 50% selectivity to methanol. Then, when we mix it with the magnesium alpha-18, then we see that the conversion is increasing, not enormously, but it is increasing, clearly showing that the further conversion of hydrocarbons is enhancing the equilibrium conversion. And then we see that we have less CO selectivity, and the methanol and hydrocarbon selectivity is higher than the methanol selectivity was before. And then we see for the product distribution, we see that we have mainly C3, then followed by C4, C2, and C5. And we see that the amount of hydrogenated products is very small. So now when we now look at the again try to compare the initial activity and the 10 hours on stream activity of these catalysts under MTO conditions and under these cold feed syngas conditions. We see that we have a higher initial rate during MTO conditions. So this is a high MTO with high pressure. So here because zero order reaction rate in methanol. But then here we see with the cold feed, with the CO2 conversion, we see that we have a lower turnover rate than what we had in MTO, but it's within the same order of magnitude. But then we also see that if we have the same amount of zirconia, we increase the amount of magnesium alpha 18, we see that the turnover rate is decreasing. And that is because it stays stable with an increasing amount of the alpha 18. On the other hand, we also see that just like what we saw from literature, the MTO catalyst under those conditions is deactivating. So the expected space-time here will be up here. After 10 hours for this catalyst, we see it's much lower, same at high pressure, whereas we see it is maintained during the tandem conditions. And we see also that after 10 hours, we see that performance is stabilizing. So we can expect that this is stable for a long time. Now, we talk too much. Let me see. So we went back. We made new catalysts. So same abundance of magnesium and silica, and compared again under methanol and cold feed conditions. And we see the same as before. The soft catalyst is deactivating much faster than the magnesium alcohol, and even more so under cold feed of methanol, CO, and hydrogen. But then, yes, and then we see that in the catalyst, we can see in yellow here, this is Raman spectra after testing, and we see in yellow, this is the silicon version, and we see that there is a high abundance of hard coke in this catalyst, which can explain why it is completed after 12 hours in stream. We have much less of that in the magnesium catalyst, but we also see that we have some occluded alkene species in the supple material, less in the magnesium alcohol, but that we have more aromatics in the magnesium alcohol material. If we now cold feed hydrogen and CO, we see that the materials are much more similar. We have now more higher abundance of carbon species in the magnesium material, and we have some hard coke in both materials, and much less of the alkenes also in the solvent. So we see that these cold feed conditions make the materials much more similar. Yes, I will just stop this, I think. Now, what happens when we compare? How do they compare under the CO2 conversion conditions? Now, first, I have to explain a little here. This is the magnesium version, this is the silicon version, and this is the CO2 conversion that we see here. And this is actually what we can say is the methanol oxidation percentage. So in the methanol conversion, yes, in the process, because when you have just we did a 3-to-1 ratio between the methanol catalyst and the MAP catalyst, and there we have 20% of methanol still in the effluent, and here we have less to start with, but more in the end in the effluent. So we can see this is a measure of how well the MAP pigments are working. Now, when we increase the amount of MAPO in the structures or in the catalyst bed, then we see that we have better performance for both materials. And then at some point, we see that they become very similar. And then we see in the end, actually, that the sample material seems to be at least as good as the magnesium material. Now, this is of course interesting, and it is interesting to find the reason why. And we went to structural analysis to elucidate this. And what we can see here is that this, from XRD, this is a perfect alpha-18, so AEI structure. And then we see in the sample material, we see that some peaks here, they are lower than they were in the alpha material. And when we come to the magnesium alpha material, we see that there's something going on here, and especially here, and also here. And this from previous analysis that we've done of integral structures of SAPO 34 and SAPO 18, we see that these extra peaks, they are actually cavasite phase. And the cavasite and the AEI structures, they are just so that the cavasite is just a double 6-ring helices, one on top of the other, whereas in the AEI structure, they are mirror images. So you have this and this and this and this. So we see now that they are that we have this distortion of this. But when we calcine the material, most of the cavasite space seems to collapse. We see here this little integral structure still. When we store the material, everything seems to vanish, and when we dry it afterwards, it reappears. We see the same for the SAPO 18 structure, but it seems more stable from this. Now, when we look at the initial performance of these materials, for the magnesium one, olefin and paraffin selectivity, we see that we have a higher paraffin selectivity in the magnesium alcohol than we have in the SAPO, and it gets lower with time. But then, if we have in situ calcination of the material, and then after 10 hours on stream performance, we see that whether we have the fresh or in situ calcine or the stored ones, we see that they perform similarly for magnesium and almost similarly also similarly. And that means that the initial state of the material after storage, it is very similar to the deactivated or state of the material after 10 hours on stream. And we can see here, am I over my time? Little bit, yes. We can see here that the freshly calcined material, it is producing lots of hydrogen to start with, and then also very much. Whereas stored material, where we have this partial collapse of the structure, we see that it is not making more alkenes, it is actually making aromatic. So we see that still the magnesium version gives a higher olefin selectivity than the silicon version, but we also see that this is more susceptible to just drop this to structural disintegration. So we see it here in conclusion of these studies. We see that the tandem operation of catalyst from CO2 to directly to hydrocarbons via oxygenate, it shows promise. But we see that the per part conversion is quite low. So that has impact for the process, of course. And then we have these potential opportunities to mitigate this challenge. And we see that in order to design the correct material for this process, then advanced characterization is functional. And I could just end this lecture by thanking you for your attention and also thanking my co-workers. And I'd like to especially tell you that Thomas and Sat in my repeat is going to give a lecture tomorrow on another system that we have been studying, and where we went all the way to process design and life cycle analysis. So that will be at 2:20 tomorrow. So thank you very much for your attention. We will get only about 15